Hello everyone and welcome back to my channel Lessons from Asha. In the previous lesson, we derived Coulomb's law for the interaction between two charges. But in real objects, there are enormous number of charges which are acting simultaneously together. So how do we calculate electric forces in such situations? In today's lesson, we will understand the principle of superposition and we will also understand how the electric forces combine in multiple charge systems. So, shall we begin?
Real electrostatic systems rarely contain just two charges. Usually, many charges act together at the same time. To study such systems, we use an important idea called the principle of superposition. In reality, every charged object contains enormous number of charges. Therefore, electric forces from different charges act simultaneously. To calculate the total force, we must combine all these individual effects logically.
We know from Coulomb's law that the electric force acting on a charge Q2 due to another charge Q1 placed at r distance is equal to k times Q1 Q2 by r square, where k is the constant of proportionality which can be written as 1 by 4 pi epsilon naught, where epsilon naught is the permittivity of free space or vacuum. We can also express Coulomb's law in vector form, and we find that Q1 Q2 product, if greater than 0, then it means the force is repulsive in nature. If Q1 Q2 is less than 0, it means the charges are unlike charges and therefore the force is attractive in nature. So, for most of the questions, for magnitude, use Coulomb's law in scalar form, and to find the direction, we have to use the fact that like charges repel and unlike charges attract each other.
According to the principle of superposition, the total electric force on a charge is equal to the vector sum of forces produced by individual charges. This means we calculate each force separately using Coulomb's law and then combine them vectorially. Electric force is a vector quantity. Therefore, both magnitude and direction are important. That is why simple arithmetic addition is not always sufficient. We often need proper vector addition. Suppose a charge experiences force due to two other charges. First, we calculate force due to the first charge, then due to the second charge. Finally, we combine both forces using vector addition.
So now let us consider the three charge systems case by case. So let us consider case 1. Here, three positive charges are lying along the x-axis, where Q1 is lying between Q2 and Q3. The charges Q2 and Q3 are such that Q2 is less than Q3. So here, the force exerted on Q1 by Q2 is written as F12, while the force exerted on Q1 by Q3 is given as F13. These being like charges, they repel each other. Hence, the force exerted F12 and F13 are repulsive in nature, and which is indicated by the arrow given in the figure. So next we consider case 2, in which 3 negative charges are lying along the x-axis, such that Q1 is lying in between Q2 and Q3, where charge Q2 is less than charge Q3. Here too, the forces acting on Q1 are repulsive in nature because all the 3 charges are light charges. Next we consider case 3, where 1 negative charge is placed between 2 positive charges along the x-axis. The charges Q2 is less than Q3. Here, since the charges are unlike charges, the force acting on Q1 is an attractive force. Next we consider case 4, in which a positive charge is placed between 2 negative charges which are lying along the x-axis, such that Q2 is less than charge Q3. Here, since the charges are unlike charges, the force acting on Q1 is an attractive force. Next we consider case 5, in which 3 charges are located at the corners of the equilateral triangle, such that all 3 charges Q1, Q2 and Q3 are like charges. Next we consider case 6, in which 3 charges are located at the corners of the equilateral triangle, of which charge Q1 is a negative charge and Q2 and Q3 are 2 positive charges. Suppose the 3 charges are kept at the corners of the equilateral triangle having side A. Then let us find the resultant electric force on a charge kept at the centroid O of the triangle. An equilateral triangle is a triangle having all the 3 sides equal as well as their angles to be equal to 60 degrees. The centroid of an equilateral triangle is the point where its 3 medians intersect. Due to the triangle's perfect symmetry, it is located exactly in the center. The distance x from the centroid to any of the 3 vertices of an equilateral triangle, where A is the side length, is calculated as x equal to A by root 3. The net force on the x-axis is cancelled by the 2 charges placed below Q1 at the point A. We know that force can have an x component and a y component. Here therefore, the x component Fx will be equal to 0. The force on the y-axis, that is Fy, is added up and we get it as Fy equal to 6k into q square by a square, where q is the charge placed at the points A, B and C, and A is the side length of the equilateral triangle. As we know that k is a constant which can be written as 1 by 4 pi epsilon naught, let us substitute this in the equation for the force along the y-axis. Therefore, we can write Fy as 6 into q square by 4 pi epsilon naught into a square. Therefore, that equates to 3q square by 2 pi epsilon naught a square. Let us consider the three charges q1, q2 and q3 placed at the three vertices of the equilateral triangle ABC such that charge q1, q2, q3 are equal to plus q. Here, the force from the vertices A, B and C, which is acting on a charge plus q placed at the centroid of that triangle, will be equal and will be also repulsive in nature. Now we consider another special case in which the charges q1, q2 and q3 are placed at the three vertices of the equilateral triangle ABC such that q1 is equal to minus q and q2 and q3 is equal to plus q. In such a case, the force acting from the vertices B and C, if a positive charge plus q is placed on the centroid of the equilateral triangle, will be equal and repulsive force. But the force from the vertex A, which will be acting on this plus q charge placed at the centroid of the equilateral triangle, will be its attractive force. So in the case of the negative charge placed at the vertex A of the equilateral triangle and positive charge placed at vertices B and C, we can explain why this resultant force becomes 0 on the charge q placed at the centroid of the equilateral triangle. For that, first we can consider the symmetry. Because of the three charges at the vertices are identical and placed symmetrically at the corners of an equilateral triangle, the centroid O is exactly equidistant from the three vertices. Whereas the magnitude of the force, we find that the electrostatic force exerted by each vertex charge on the centroid charge has the same magnitude. Then we consider the direction of the force. Here, the three equal forces point toward, for or inward along the lines connecting the vertices to the centroid. As a result, they make an angle of 120 degrees with one another. When three equal forces are oriented at 120 angles in a plane, their vector sum always cancels out perfectly to 0.
In electrostatics, we often study special arrangements such as charges placed along a line, on a ring, or over a surface. These arrangements help simplify calculations and reveal deeper physical patterns in cases like solid sphere, metal rod, thick lamina, and circular metallic ring. The principle of superposition becomes the foundation for many advanced electrostatic concepts, including electric field, electric dipoles, continuous charge distributions, and Gauss law. So far, we studied electric force between charges. But another fascinating question now arises. How do charges influence the space around them? That leads us to the concept of electric field in the next lesson.
So today we understood how electric forces combine together in multiple charge systems. Using the principle of superposition, we also calculated complex electrostatic systems in a step-by-step manner. This idea becomes very important for understanding all the advanced topics in electrostatics. So, in the next lesson, we'll move beyond forces and we'll try to understand how electric charges create electric field around them. So, thank you for learning with me today, and I'll meet you in our next lesson.
If you found this explanation helpful, do like, share, and subscribe to the channel for more simple and interesting physics concepts based on the NCERT syllabus. So, see you in the next lesson. Until then, bye bye.